Welcome back, ladies and gentlemen. I hope that you found things with the velocity quiz successful. I hope you found that pretty straightforward, easy to do. Today we are going to be tackling acceleration, probably the single most complicated idea in physics. Now I say that, but at the same time it's not actually that complicated. It's just very abstract. What do I mean by abstract? Well, like concrete, is something you can touch and see and smell and hear. Abstract is something you can only picture in your mind. And acceleration is one of those things that you can't really see it. Not really, like you sort of can. But let's talk about what acceleration is, right? So first things first, right? We have our notes. We should be here on about page 25 or so. And we're dealing with acceleration. Now, acceleration, as we well know, is a vector. So you can circle that, highlight that, or just note that down on a piece of paper. And it tells us here that acceleration is the change in velocity over time. That's our definition, and that's going to be pretty critical for us. Velocity over time. Now, the units for acceleration are going to be meters per second squared. Or, there's another one. Meters per second over seconds. That one will make a lot more sense once we take a look down at the formula, which is just the very next line. Acceleration equals delta V over delta T. We remember deltas. We've seen those before. We know what they mean, right? Delta means final minus initial. So this is the same as writing VF minus VI over TF minus TI. Now, you put all this together, and what is this telling us? Well, look at the definition. Velocity over time. Velocity over time. Look at the units. Meters per second are the units of velocity. Seconds is the units of time. So the units for acceleration are velocity over time. We can also write this as meters per second squared, because seconds squared means that you've got like 1 over s times 1 over s. Some of you are looking at that going, okay, that made perfect sense. Some of you are looking at that going, that was all a bunch of gobbledygook, doesn't make any sense to me. That's fine. But let's explore, right? We have our basic formula. Here it is. We're going to have 4 different numbers in order to find this A thing. But what does it do? How does it work? Well, the key thing, as it tells us here, is that the velocity has 2 parts, magnitude and direction. And we know that, right? Every vector has magnitude and direction. So let's pretend that we've got a starting value here. We'll do a starting example here. We're going to go with the example here of 5 meters per second north. Now, this is not an acceleration, this is a velocity, right? But we're said that we're dealing with changes in velocity. That is the definition of acceleration, a change in velocity. So, what are all the ways that I can change this velocity? Well, my first option is that I change the number. I can change the number, or I can change the direction. Either one will mean that this is different. So, let's start by changing the direction. I'm starting at 5 meters per second north. Okay? So if I say that north is this way on your screen, that means that I'm going at, some pace like so. But if I'm going to change the direction, maybe instead of going this way, I go that way. The number stays the same, it's still 5, but the direction I'm traveling will be different, and that means that there was a change in velocity, because I went from going this way to going this way. That's a difference. So this 5 meters per second north could become 5 meters per second south. That's a change. Something is different. Now, the number is the same, but that doesn't matter. For the purpose of acceleration, it just means there has to be a change in velocity, and the velocity has two things. I can either change the number or I can change the word, the direction. I went from north to south. That's a change, therefore there was an acceleration. So that's the first one. The second one, velocity can be changed by increasing or decreasing the magnitude, the number, right? Because logically, if I've changed the direction, my next option is to change the number. So instead of it being 5, maybe it's 4 or 6, right? Both of those are a change. 5 to 5 isn't a change, so that doesn't count. So there has to be some kind of change. So let's take a look at the example that we've got in our notes, okay? You guys already have it written down. I'm going to work through it though because I want to be able to talk about it. So, first things first. Let's take a look at our first example. The one we've got here is a longboarder, a skateboarder. So the skateboarder is going to be moving along at a velocity of 1 meter per second, it says. So we're going to have here our example number 1, and we're going to have a guy on a skateboard. And you guys are going to get to see that I can't draw. So we're going to give him a hat. There we go. And he's going to be moving along with an initial velocity of 1 meter per second. Now, the 1 meter per second, it does explain then that after 3 seconds his velocity is 6 meters per second. So something is going to happen here. So he's starting with this, and then his final velocity, it says, is 6 meters per second. And it says that this whole thing is going to take 3 seconds. Okay. So we've got our 3 seconds to go from one number to another. Let's see. We've collected all our information. Remember our format, right? This is the given. Then we're going to do the formula. Well, our formula is A equals delta V over delta T. Now, if you want, you can expand that. You can write that larger. You could write it like this. A equals VF minus VI over TF minus TI. Now, obviously, the big problem with this is that, this is more stuff to write. This and this mean the same thing, but this only makes sense if you already know what triangle means, right? If I know what the triangle is, then I don't have to write this because it's already built into this. But if you don't remember, that's fine. Go ahead. Do it longhand. There's nothing wrong with that. Finally, we ought to do the calculations. Okay, so the calculations, A is going to equal to, I got to make sure I map them properly. VF is this one. So that one's going to be plus 6 minus plus 1. The biggest problem with this is the same as the other stuff we've seen with time or displacement, is people flipping the two of them around. Now, time, I've just got 3 seconds here. I don't have a TF or TI. But we saw this when we were doing the time unit. What we're dealing with here is just that it's going to take us 3 seconds to do the whole thing. So that means that the initial time was 0. And then the final time is 3. So, 3 minus 0. There it is. Finally, we're going to solve this. So we're going to get 5 divided by 3, because it's 6 minus 1. Now, in physics, we don't generally do fractions that much because, stuff's hard enough as it is. So we usually put a final answer. So this would be in 1.66 meters per second squared, and this will be positive. So I think we can safely say that this guy on the skateboard got faster, right? He started off at 1, and now he's moving at 6. So obviously that's faster. He hasn't changed his direction. His direction has remained the same the whole time, positive, which for our purposes we said is this way across the board. So his direction stayed the same, but his magnitude did change, which means there must have been an acceleration. And there it is, 1.66. What this would mean if we had an example is like, here's our skateboard, the eraser skateboard, and it's going to start here. And, you know, it's starting off pretty slow, and then it gets faster and faster and faster until it's racing across the board. Now, when I said that this stuff is more abstract, that's because it's harder to see acceleration. You guys could see that this eraser started over here and ended over there. That part's easy, right? That's position or displacement. You could also see that it was moving slow or fast. You could see, okay, at the start it wasn't going very fast, and then towards the end it was going much faster. But the change from slow to fast, that's a lot harder to map. That's a lot harder to keep track of. And that's, you know, why acceleration is a little more abstract, a little bit trickier to work with, because you can't easily see it. You could tell somebody, oh yeah, that thing's getting faster, if you watch it for a long time. But you can't tell just like, oh, faster. You can't. You can tell that it is fast or slow, but you can't tell if it's getting faster unless you compare the initial to the final. You need these two things that you can compare in order to make sense of it all. Okay, so there's our first example. Let's take a look at another example. The next example is going to be a dog. Okay, so now you guys get to see me attempt to draw a dog. I apologize in advance to all the dog lovers out there. So we're going to make what I call a squiggle dog. And to make sure that everyone knows it's a dog, I'm going to make it say bark, because otherwise you wouldn't know. So there's our squiggle dog. And it says that our squiggle dog is running towards the road with a velocity of 3 meters per second. Okay, so the initial velocity of the dog is plus 3 meters per second. And then it says that it's 6 seconds later, it stops at the edge of the road. So the time is 6 seconds. And then the final velocity, well, it kind of tells us what it is, but it also kind of doesn't, because it just tells us that it stops. For something to stop, that means its velocity has to be 0, right? That's the definition of stop. There it is. Okay, so we've got our numbers, and we have our formula. So let's plug in our numbers here. So we've got A equals, now our initial velocity is 3. The thing that people want to usually do is they put 3 right there. But that's not what goes there. It's final minus initial. So this is 0 minus plus 3 over 6 minus 0. Because remember, the initial time is just going to be 0, because that's where we're starting. So, well, that looks weird, doesn't it? Right? Like we got a 0, then a 3, then a 6 minus a 0. Again, the hard part for this is always just going to be keeping everything in one place, keeping it organized. This is why you write down the givens, then you write down the formula, then you fill in the formula. Because let's say, you know, you mix this up. Let's say you put this in the wrong way. You can find out more easily because you can check. You can be like, okay, I put these in the wrong spots. I can look from here to there and make sure that the symbols all match. So when we finally do this, we're going to get that this is going to be negative 3 over 6, which is the same as negative 0.5 meters per second squared. So what is that showing us here, right? Well, this dog is clearly slowing down because it's going from 3 to 0. And we see that in the acceleration. Look, that's negative 0.5. The skateboarder was getting faster, right? He went 1 to 2. And over here we see that it's 1.6. Okay, so there's a pattern emerging, right? We can see that there are certain things that happen, and we can work with that. And that's what our notes say on page 26. So it looks like the negative acceleration means slowing down, and positive acceleration means speeding up. But that's not actually true. We have a third example here, because this is what we call a discrepant event. It's a big fancy way to say that something isn't going to quite follow our pattern. And that means something, as we're going to see. So, let's see. I'm going to erase a bunch of this information here. We got to keep the squiggle dog, though, and the skateboarder. I mean, they're just too cool. You can't get rid of them, guys. Don't get rid of them. And we're going to work over here. On this side of the board, and we're going to work through our last example. Okay, so our last example is a man on a bicycle riding with a velocity of 5 meters per second, and it says he's riding west. That is key. So if he's riding west, that means that he is going to be, let's say, here. So So we'll just, let's see if we can remember how to draw a bicycle. Oh my, it's been a while. Let's see. We're going to go like this, like this. There we go. And we'll move some handlebars, and then the man will be sitting here. He's holding the handlebars. And of course, he's wearing a bike helmet because he spent a lot of time making his brain really clever. We got to make sure that he keeps it in one piece. So there he is, and he's driving west, which is going to be a negative direction. And it says here that his initial velocity is 5. So this is negative 5 meters per second. And this is VI. And then it says that over the next 5 seconds, he increases his speed to 10. Okay, so VF is negative 10 meters per second. And the time is 5 seconds. So what's happening? Okay, well, we've got our given. So then we're going to write down our formula. I'll just squeeze it over here. A equals VF minus VI over TF minus TI. Put some arrows on there because they're vectors. I start filling in the numbers. A equals VF is minus 10 because it's west minus negative 5. Oh boy. Divided by 5 minus 0. Minus negative 5. How do we do that? What happens? Well, hopefully you guys remember that minus negative 5 is the same as me writing negative 10 plus 5 over 5. So negative 10 plus 5. Remember our algebra, remember our math class. It's going to be negative 5 over 5. So that means the final answer is going to be negative 1 meter per second squared. Okay, wait, what's going on? It's negative. With the dog, negative meant I was slowing down. But with this guy on the bicycle, negative, I'm not slowing down, I'm speeding up. Right? Like 5 to 10, that number's going bigger. A bigger number means I must be speeding up. So this is weird. Let's map it out. This guy over here was speeding up. And if you can remember, I know this was a long time ago, his velocity was a positive number. And this guy over here had a positive acceleration. Okay? So he was speeding up, positive, positive. This guy over here, we'll do it in green, was slowing down. Squiggle Dog was slowing down, and it had a positive velocity and a negative acceleration. But what about this guy? This guy's getting faster. He goes from 5 to 10. So this guy's speeding up. And if I do the same map, I get that the velocity here is negative, my bad. The velocity here is negative, and the acceleration is also negative. There's one thing missing here, isn't there? There's one combo of velocity and acceleration that we don't have an example for, but I'm pretty sure you can guess what's going to happen. We've got positive, 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 negative, negative, negative. What's this got to be? Positive acceleration. Negative velocity. And what's going to happen there? Take a look at the pattern. If you're speeding up, what do you notice? What is similar? What's the same? If you're slowing down, What do you notice? Two that make you speed up, two that make you slow down. Now you have space to draw this out, and you could draw it a number of ways. We're going to keep it like this, even though it's not the best possible one. But what are we trying to see here? Well, remember, positive and negative means direction in physics, right? Positive direction, we could say, is, well, this way. Negative direction is that way. If that's the case, this guy's speeding up going west. These guys were going east. He's speeding up going east, he's slowing down going east. So this guy here would be slowing down going west. Now all of that's fine, but what's the key point? What is the key thing that we're trying to see here? Well, negative and negative, I get faster. Positive and positive, I get faster. It's like the acceleration is helping the velocity, it's adding to it, either by making it more and more positive or making it more and more negative. Down here, we get the opposite. Down here, the acceleration and the velocity are fighting each other. In this case here, the velocity is trying to go this way, and the acceleration is putting the brakes on, trying to make it go backwards, trying to slow it down to stop. And here we get the same thing. I'm trying to go this way, but the acceleration is pushing back against me, forcing me to get slower and slower and slower until I stop. So, if we summarize this, what do we get? Very simple rules. If the signs are the same, you speed up. So that means positive and positive, or negative and negative. If the signs are different, you slow down. So positive and negative, negative, positive. So, as you can see here, changing the velocity has only a few possibilities. We've got this map here that I've just finished filling out, and you can either speed up or slow down, depending on if the signs are the same or if the signs are different. And then there's the other one that we talked about right at the start. You can either change direction. So we'll toss that on the top here. And that's it. These are all the ways that the velocity can change. These are all the ways that we can have an acceleration. Our first option, change direction. Go from, say, north to south. The number stays the same, but we go a different direction. Then option 2, we can have a change in the number because it speeds up. The signs are the same, both positive, both negative. And then finally we've got option 3. The signs are different. Now I'm going to slow down. And that's it. Those are the 3 things that you need to know about acceleration. Speeding up, slowing down, or going a different way. So there we go. Now, I know this is a little abstract and there's an awful lot of stuff here. Obviously, we used a lot of examples in order to explain this. You guys have a whole bunch of examples on the next several pages of your booklet. Everything up to page 30, from this point onward, 25 to 30 or so, is about acceleration. And it's such an important topic that I'm going to give you guys a quiz on just acceleration. Okay? So, spend some time, work through these. All of these questions have answers. You can see what the answers look like as you are working. You can double check, see how you're doing. Ask questions if you're stuck, and enjoy some time outside. It's pretty nice. Make sure you guys, of course, keep your social distancing, but enjoy the nice weather while we have it, okay? Obviously, this idea, pretty significant. This is used in a lot of things. So do the best you can and ask questions. And in the meantime, guys, stay safe.